Suppose that 50% of the cars sold in the United States are made in the United States, 30% are made in Japan, and 10% are made in Germany. We know that this is not a valid assignment of probabilities. I mean, so far it's okay, but we don't know anything about the other 10%. So we need 100% when we add it up. So because it doesn't have all 100% of the cars, then therefore it doesn't work out. So now that last 10% we will assume is made in other countries, and then it's a valid assignment of probabilities. What we would probably do is we would probably make some sort of table to make it easier on us. So we would say make of car and probability. The United States has 50%. We would say Japan has 30%. We would say Germany has 10%. And then we would say other also has 10%. So this is the probability distribution, and unfortunately I wrote it in the wrong spot, but there it is. Probability distribution lists all the outcomes and their probabilities. So that is a probability distribution. What is the probability that a car selected at random is not made in the United States? Well, in order to make our lives a little bit easier, I'm just going to copy and paste this so that we see it on our screen at all times while we're doing this. What is the probability that a car selected at random is not made in the United States? Well, if it's made in the United States and we know that that's 1/2 of them, we take 1 minus the probability that it's made in the United States, because 1 minus the probability that something is the probability that something isn't. So 1 minus 0.5 gives me 0.5. So the probability is 0.5. And notice that's what happens when we add up all of the other probabilities that are not American-made cars. What is the probability that a car selected at random is made in Germany or Japan? So the probability of Germany or Japan is the probability of Germany plus the probability of Japan. And we know that because they are disjoint events. This rule only works for disjoint events. We know these are disjoint because a car cannot be made in both, or at least the make of the car cannot be both German and Japanese. So that's why we know it's disjoint. Now, technically, could parts be made in one country and another part be made in another country? Yes, but when we're speaking of make of car or where it's made, we're typically referring to the type of automobile. So a German automobile or a Japanese automobile or an American automobile. So Germany is 0.1, Japanese is 0.3. So the answer is 0.4. What is the probability that two cars that are selected at random are both from Japan? We're going to use the multiplication rule here because we're talking about multiple events in a row. And in this case, we're going to treat them as independent, even though technically they aren't. So you can read what it says. Basically, if the population size is greater than 10 times the sample size, we treat them as independent in statistical analysis. And we, even when we're sampling without replacement. So let's say there are 1 million cars. Well, the probability that a car was Japanese was 30%. So that's essentially if there were 1 million cars, and there are actually more than that. That's basically saying that 300,000 out of 1 million is the probability of the first one being Japanese, and 299,999 out of 999,999 would be the probability that the second one is Japanese. Now notice that while this is technically not the same as 3/10 times 3/10, it is awfully close. So it's very close to 0.3 times 0.3. And so this is why this rule exists. We treat them as independent, even though they technically aren't, because when the population size is so large and the sample size in this case is 2, notice that we're only taking 2 cars. Since the population size is very large, the sample size is very small, we can treat them as independent. So 0.3 times 0.3 gives us 0.09. And from the mathematical statistical verbiage, we would say the probability of Japan and Japan given 2 cars. So that's the same thing as the probability of a Japanese car times the probability of a Japanese car. What is the probability that none of the 3 cars, if we're sampling 3 cars? So the probability that none of 3 cars came from Germany. So in order to figure this out, we have the probability of a German car is 0.1. So the probability that it is not a German car is 0.9. So essentially what we need here is the probability that we have 3 cars, not German, and not German, and not German. So in this case, that's going to be 0.9 times 0.9 times 0.9, because once again, we're treating all of these as independent. So that's 0.9 to the 3rd power, which is 0.729. Okay, part G. What is the probability that at least one of the 3 cars, so again, we're having 3 cars selected here, is made in the United States? So if a car is being made in the United States, the probability that we have an American car is 0.5. Now, the probability that at least one of the 3 cars is made in the US, the easiest way to do this problem is to say 1 minus the probability that none of the 3 cars is made in the United States. So if we have trying to figure out the probability that none of 3 cars is made in the USA, since we're treating these as independent events, that's the same thing as probability of not USA and the probability of not USA and the probability of not USA. So in this case, since they're independent events, we can say that's 0.5 times 0.5 times 0.5. So the probability that none of the 3 cars is made in the United States is 0.125. If we want the probability that at least one is an American car, that's 1 minus 0.125 or 0.875. Once again, these problems come up a lot. There's definitely going to be a problem like this on your test. In order to find the probability of at least one, you want to do 1 minus the probability of none. You do not want to do the probability like we did that none of 3 cars came from Germany up in part F. That's not the same type of question, because if none of the 3 cars came from Germany, it's possible that 1 of the 3 cars did, or 2 of the 3 cars did, or 3 of the 3 cars did. And you would have to do a lot of calculations. If I were doing part F in a slightly alternate universe, and it said, what is the probability that at least one came from Germany? All I would have to do is 1 minus 0.729, because this is the probability that none of them came from Germany. So if I did 1 minus 0.729 and I got 0.271, I think it is, that would be this alternate universe problem F, because all I have to do is find the probability of none of them and then doing 1 minus that. H, what is the probability that the first time you get a Japanese car is on the 4th selection of cars? So basically a problem like this is saying I'm going to start choosing cars. And once I get to a Japanese car, then I have now figured out that that's my first Japanese car. So in the first case, I could get a Japanese car on my first choice. That would be 0.3. However, there's also a 0.7 chance, or the probability of 0.7, that I don't get a Japanese car. So basically, here's a table of what's happening. On the first choice, it could be Japanese, or it could not be Japanese. On the second choice, oh, my fault. On the second choice, if I got a Japanese car on the first choice, I don't have to continue doing this problem. So on my second choice, if it was not a Japanese car, then I have to continue doing this problem. And so then it would be 0.3 or 0.7 again. If on the second choice I get a Japanese car, I am then done. So if I got it on the first choice, I don't have a second or a third choice. If I got it on the second choice, I don't have a third choice, and so on. So then this one gets split into 0.3 and 0.7. So basically what happens is I only continue choosing if I didn't get a Japanese car last time. So that means that the first selection was not Japanese. The second selection was not Japanese. The third selection was not Japanese. My fourth selection is Japanese in this problem, so I'm going to figure out the probability that this occurs. That would be 0.7 to the third power times 0.3. So that ends up being 0.1029. 0.1029. Letter I. What is the probability that two cars selected at random are both from America or both from Japan? So the probability of US and US or Japan and Japan. So probability of US and US would be 0.5 times 0.5, or, which means since we're going to use the addition rule with an or, plus probability of Japanese and Japanese. This ends up being 0.25. This ends up being 0.09. If I add these together, I end up getting 0.34. Probability rules. Let's go over some probability rules a little bit. For any random phenomenon, one more time, each trial generates an outcome, and an event is any set or collection of outcomes, and the sample space is the collection of all possible outcomes. We've talked about sample spaces a little bit, but here's another example. If a family has two children, the sample space is boy, 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 girl, girl, boy, or girl, girl. In this case, all four outcomes are relatively equally likely. If you are dealt 5 cards from a deck and you record the number of aces you get, what is the sample space? So in this case, the sample space would be 0, 1, 2, 3, or 4. There are 4 aces in a deck of cards. So if you get 5 cards from a deck, you can't get 5 aces. These outcomes are not all equally likely. It is much more likely that you get 0 aces or 1 ace than you get 4 aces. That's why if you're playing poker and you get 4 aces, you will probably win the hand. It is unlikely that somebody else would have a better hand than you. Whereas if you get 0 or 1 aces, then your hand is very common, very normal. When all of the outcomes in the sample space are equally likely, kind of like this 2 children situation, then the probability of an event is the count of all the outcomes in A, which is the event that we care about, divided by all of the possible outcomes. So, what is the probability that we have one boy and one girl in this example? That would be 2 out of 4 because there are 2 outcomes that have one boy and one girl out of 4 total possible outcomes. The probability that a family with 2 children has 2 boys is 1/4 because there are 4 outcomes and one of them is 2 boys. But the probability of getting 4 aces in 5 cards is not 1 out of 5. So notice that even though there's 1 out of 5 outcomes that has 4 aces, since all of those probabilities are not equally likely, I can't just say 1/5 because there's 1/4 out of those 5 numbers. So I have to be a little careful when I'm doing problems like this. What is the probability of drawing a single card from a deck and getting a red card or an ace? Now, if you don't know anything about a deck of cards, a deck of cards has 4 suits. There are spades and clubs. Those are both black cards. And then we have hearts and diamonds. Those are black cards. There are 13 of each type of suit. So there's an ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, a jack, a queen, and a king for each of these 4 sets. So there's 13 times 4, which is 52 cards in a deck. So each of these suits has an ace. So there are 4 aces. There are 26 red cards because there are 13 hearts and 13 diamonds. So there are 26 total red cards. So we would think that the probability of drawing a single card from a deck and getting a red card or an ace is the probability of getting a red card plus the probability of getting an ace. So that's 26 plus 4, or 26 50 seconds out of 4 50 seconds. However, that would not be correct because we have to note that there are 2 cards that are red aces. So basically what happened was we counted all 4 aces, then we counted all 26 hearts, diamonds, all 26 red cards, and we actually counted these 2 cards in both situations. So those 2 cards are actually getting double counted. What we want to do is we want to subtract the probability that we have a red ace because we already counted both of those cards twice. So we have to subtract the 2 cards we double counted, and we end up with 28 out of 52 as our final answer. Now that can be reduced to 7/13, but I'm not going to write it down because I ran out of room. To answer this problem, we need the general addition rule. So that is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both. That's because the both is double counted. And one more note, when we use the word or, we mean it in the inclusive sense. So when we say or, we're saying red or ace or both of them. That's why we have to subtract the both because those were counted twice. So that's what or means in statistics. We can now answer that question from earlier because we have an extra piece of information and we have the general addition rule. Probability of being in statistics or having a TI calculator is equal to the probability of being in statistics plus the probability of having a TI calculator minus the probability of being in statistics and having a TI calculator. So we have 75% being seniors, 90% having a TI calculator, and 70% counting in both. So that would end up being 1.65 minus 0.7. So that's 95% of all of them.